All right, let's begin our talk. In this talk, we let Mn be a smooth, complete manifold without boundaries, and a family of embeddings, or more generally immersions, phi, they are said to satisfy the mean curvature flow if they evolve according to the following PDE system. Well, geometrically, let's say if we just consider the one-dimensional case, then we have a curve, let's say a curve embedded in R2, then we can, figure out the mean curvature vector at each point along the curve, and we basically want to deform the curve according to in the direction of the mean curvature vector. And the same idea applies to higher dimensions. So this is the mean curvature flow. And how do we sort of understand it? Well, if we pull back the ambient metric, the ambient Euclidean metric onto the surface to obtain a metric G, then we see the mean curvature vector is basically the Laplace operator acting on the embedding phi. However, because the Laplace operator depends on the evolving metric, so even though this equation looks like a heat equation formally, but really there's a hidden nonlinearity due to the dependency on the metric GT. And if we rewrite this equation in local coordinates, we see this is in fact a quasi-linear parabolic PDE system. Okay, so this is mean curvature flow. Now let's look at some of the basic examples. Well, the first example would be the minimal surface. They have zero mean curvature, and therefore they are stationary solutions of the mean curvature flow. And the second example is the circle. So we have a circle here. Well, because of the symmetry, right, at every point the mean curvature vector points towards the origin, then there's the mean curvature flow PDE is really reduced to an ODE, and we can just solve for the radius RT and realize that the radius must evolve according to this function. So geometrically, at a later time, the circle has shrinks to a smaller circle, and in finite time, it shrinks down to a point. And the same picture applies to higher dimensions. And again, we can solve for the radius, and we realize that a round sphere will disappear to a point in finite time. And we can also take products of the spheres and the Euclidean space to obtain generalized cylinder. So here, let's just draw S1 cross R. And we realize the Euclidean factor doesn't change, but the spherical factor shrinks under the flow. So at a later time, it becomes this, and eventually collapse down to the Euclidean factor in finite time. Okay, so these are three simple examples. Now, let's move on to some facts about the mean curvature flow. Well, first of all, suppose we consider the mean curvature flow of either closed hypersurface or non-compact hypersurface with well-behaved infinity. Then we have, in fact, short time existence and uniqueness to our mean curvature flow solution. And in fact, it's also smooth because the parabolic nature of the PDE, the smoothing properties. Now, if we vary the embedding according to direction x, then one can compute the first variation and realize that this is the first variation. And now because of the minus mean curvature vector term here, this tells us that the mean curvature flow, in fact, is the negative gradient flow of the area function. Yeah, so this gives it a variational structure. While the third one is the avoidance principle, which is a consequence of the maximum principle for the mean curvature flow equation. But geometrically, it has a sort of nice statement here, which says if we have disjoint hypersurface to start with, and we run the main curvature flow on these hypersurfaces, then these hypersurfaces will remain disjoint under the flow. So here's the intuitive picture. Suppose we have two hypersurfaces. I'm just showing a curve here. And let's say at a later time, okay, they start out as disjoint, but let's say at a later time, they touch somewhere. So somewhere here. Now, at the point where they touch, we can see the mean curvature vector of the orange curve has a larger length than that for the red curve. Then this is telling us that we have something that's moving slow, but it's catching up to something that's moving fast. That's not possible. Okay, so that's the idea behind the avoidance principle. And it has a very nice consequence, namely that if we have mean curvature flow of any compact hypersurface, right, it might look something funny. Well, this is not too crazy. But then we can always bound it, or we can enclose it inside a large sphere. Now, because the sphere has to disappear in finite time, then the orange surface, evolving by mean curvature flow, can also only exist for a finite time. Okay, so this, all right. Having gone over some basic facts, now let's look at some special class of solutions. The first is the so-called self-shrinking solution. So what are they? Well, suppose we have a hypersurface satisfying the following elliptic PDE, then we can actually use it to construct a solution to the mean curvature flow. What do? We just multiply it, or we rescale it by this time factor, and we end up getting, so the whole thing is a homothetically shrinking solution to the mean curvature flow. And what are some of the examples? Well, we've already seen spheres and cylinders, and then there's also something called self-shrinking torus. I'll just quickly motivate it. Now, suppose we have, let's just consider S1 cross S1. Suppose it's a fat torus. Then, under the flow, it's trying to fill the hole in the middle. Now, suppose the torus is sort of skinny, looks like a ring. Then, due to the small S1 factor, it's going to shrink down to a circle, right? Now, if the two circle factors try to balance each other out, then there should be some intermediate configuration that neither wins in this game, so it remains a torus and until it disappears. Okay, so the one in the middle is the one actually constructed by Angerland. Okay, so this is a self-shrinking torus. And so these three examples, sphere, cylinder, and torus, they are embedded. There are also immersed examples. So for example, a curve like this is one of the Albert-Schlange curve in R2, it's immersed. There are more curves with other symmetries, so sort of more pedals. And of course, we can also construct higher dimensional immersed examples simply just by taking the product of these curves with RK. Okay, so some examples. All right. Another important class of solution to the mean curvature flow is the so-called translating solution. And what are they? Well, suppose we fix some direction V in Rn+1, and we have some hypersurface, our surface satisfies this elliptic PDE. And then we can actually construct a solution to the mean curvature flow simply by translating the hypersurface in the direction of V. And this way, we just get a solution to the Minkowski flow. So what are some examples? Well, the first example is the so-called Grim Reaper. It's a curve in R2. And let's say this is the time t equal to 0 slice. So asymptotically, it's approaching two parallel lines. And it's also translating to the positive axis, yeah, with unit speed. So this is at later time. Okay, so this is the Grim Reaper. We can also take the product of the Grim Reaper and RK to get the so-called Grim Reaper hyperplanes. But on the other hand, in higher dimensions, there are also another class of translating solutions. They are rotationally symmetric. Well, the Grim Reaper hyperplane, they are not, but this so-called bow soliton is. So let me again try to draw it. So let's say this is the y-axis, and we have some p as a function of x here. Okay, and we just rotate around the y-axis. We obtain some paraboloid-shaped surface, but it's not quite paraboloid because the profile function p here, yeah, it's the solution to the following ODE initial value problem, and we can actually solve it uniquely and well, not so explicitly, but on the other hand, we can understand its asymptotic behavior as we approach spatial infinity. Namely, it's quadratic up to a log correction at infinity. Okay, so this is the picture of the bow soliton. And again, under Minkowski flow, the bow soliton in this case it just moves, yeah, to the positive y-axis. Okay, all right. So two class of solutions. Now, in terms of these solutions, so how do we sort of understand them? Well, okay, so if we try to keep track of how the geometric quantities of the hypersurface evolved under the Minkowski flow, for example, the second fundamental form, then we realize the following, right? Suppose we consider a solution, a smooth solution that's existing on a maximal time interval, 0 to capital T. If we have finite, if capital T is finite, so we have a finite time maximal solution, then we say this finite time solution is type 1 if the maximum or the supremum of the second fundamental form, it blows up at the rate square root of t minus t. It's given here by this definition. And we call that type 2a if the blow up rate is faster. And on the other hand, if we have sort of if the maximal time interval is from 0 to infinity, then we say the solution is type 3 if the highest curvature grows or on the order of square root of t, 1 over square root of t. Okay, in this case will be decay. Well, and or we call the solution to be type 2b if the highest curvature is on the order higher than square root of 1 over t. Okay, yeah. So these are the two. So in this talk, we'll be mainly focusing on type 2a, but for completeness, let me mention 3m 2b here. Okay, so with this definition in mind, we can ask some questions, and we also, sorry, yeah, let me cross that out. We can also provide some quick answers. Well, the natural question is that does each type of solutions exist, or do they exist? And if so, what can be said about, say, for example, blowup rates of the type 2A and type 2B? Because for type 1 and type 3, the blowup rates are already given, yeah? But for the 2A and 2B case, there's much more freedom. And also, what if we have such solutions, what can be determined about the precise asymptotic behavior for such solutions near the maximal time of existence? So these are natural questions. And to give some simple or maybe a quick example to these questions, we have the following. So for type 1, any self-shrinking solution, in fact, is a type 1 solution. And we also see that any translating solution will be an example of type 2B solution. If we consider an entire graph with linear growth at spatial infinity, then the classic result of Ecker and Huiskin says that such a solution must be type 3. And for type 2A, we will, in the rest of the talk, we'll see more examples of type 2A. Okay? And having given these examples, let me also say a bit more about this question, because somehow this is basically asking for what can we say about the sort of how do we understand singularities for mean curvature flow. So this brings us to the topic of blowup analysis. And what does it say? Well, it basically, the rough idea is the following, right? Suppose we have suppose the mean curvature flow has a type 1 singularity. And what can we do? We can pick a sequence of points and time, and we then, well, because it has a type 1 singularity, then we definitely find such points and times where the curvature blows up. Now, we basically want to use these larger and larger curvatures as scale to rescale or to rescale our solution. And what do? We basically want to magnify the space by a factor of 10 and magnify the time by a factor of 100. And this is so-called parabolic dilation. And precisely, this is how it's done. And the minus phi here is just centering our surface at the so that it contains the origin. And after the parabolic dilation, now we have a family of spaces or hypersurfaces. Now, we can then apply compactness theorem to obtain that along the subsequence, yeah, there's a limit. These phi i's converge to a limiting geometry, which will be called a sort of pointed singularity model. And in particular, because of the way we are doing dilations here, the limiting space is non-flat. Okay, so this is the rough idea of the blowup analysis. What it really does is it's basically you want to magnify or sort of zoom in around a point of chi curvature and see what it looks like. And with this procedure in mind, Huiskin was able to show that type 1 singularities in mean convex mean curvature flow, they are modeled by self-shrinking soliton. And one can work out a similar procedure for type 2A singularities for mean convex mean curvature flow, and then to see that they are modeled by translating soliton. Okay, and this is the work done by Huiskin and Sinistrari, towards the end of the 90s. Okay, but then this doesn't quite tell us whether or not type 2A singularities would exist at all, okay? Because this result here just says, if it exists, then after blow up, you see a translating soliton. Now let me move on to give you some existence results concerning the type 2A singularity in mean curvature flow. Well, first, let's look at the one-dimensional case. And, that is the mean curvature flow of planar curves. If we consider embedded curve in R2, then it turns out there's no type 2A singularity at all. And this is the result by Grayson and Gage and Hamilton in the 80s. because Grayson has proved that any simple closed curve, right, no matter how complicated it looks like, it might look something like this. Then eventually it will unwind itself into something convex. So this is by Grayson. And then by Gage and Hamilton, this will shrink down to a point. And after you blow it up, you see a round circle. Okay, so this is the result in for embedded curve in R2. No type IIa singularity. On the other hand, if we consider immersed curve in R2, then Angen and Velasquez was able to construct example or construct a solution that does develop a type IIa singularity. They start out something like this. Yeah, cardioid, and the smaller piece here will basically shrink into a cusp in finite time. And if we zoom into the cusp, we will see a Grim Reaper. Okay. So that's the idea. Yeah, and also they were able to obtain some precise asymptotics concerning the for such solution. Namely, the highest curvature blows up at this rate, and in particular, it is faster than a type I rate, but slower than any higher polynomial power. Okay. Yeah. So this is for type IIa singularity. That's the one-dimensional case. Now, what about higher dimension? Well, for higher dimension, it turns out in the embedded case, there will be type IIa solutions or type IIa singularity. So let me motivate it through the following example. So if we consider a family of spheres, then what do we know? So if we have loose cinching, so it looks something like this, then by Huiskin's classic result, it's going to, it's going to disappear in finite time in a sort of round fashion. And after blow up, we actually see a round sphere. If we have very tight cinching in the middle, so we start out with some kind of a dumbbell shaped, then at a later time, the middle part will pinch off before the two ends disappear. And yeah, it's going to pinch off. Now, if we take our sort of a magnifying glass and we try to zoom in the middle, what do we see? We will see a cylinder. And again, this scenario was analyzed by Huiskin. Basically, he showed that, well, in fact, when you have this kind of neck pinch singularity, the singularity forms at a type I rate, and you blow it up, you always see a cylinder. And it's then called a non-degenerate neck pinch. And it turns out that there's some intermediate case between scenario 1 and 2. Namely, it still looks something like this, but it doesn't. So this is a mean convex but a non-convex solution. But it's possible that it just disappears into a point. And depending on where we base our point to carry out the blow-up analysis, we will see different singularity models. So we'll see a more detailed analysis later on. But here, let me just say that for the critical case, Altshuler, Angen, and Giga carried out a qualitative study, and they proved that this scenario exists, and it gives you a type IIa singularity. A more quantitative analysis including the precise blow-up rate and the precise asymptotics near the singular time was later carried out by Angen and Velasquez, using a different method. All right, let's look at the theorem by Angen and Velasquez in detail. So they have showed that for each integer m greater or equal to 3, and let's actually here assume m is also even, there exists a rotationally symmetric mean curvature flow on the sphere of dimension 2 or higher, such that the solution has a degenerate neck pinch in finite time. Okay, so the solution looks something like this. Looks like a peanut. And it comes in 3 regions: tip, intermediate, and neck. Okay, and it's reflector symmetric, so I'm not drawing the other side. And here, yeah, the tip, intermediate, and neck. So what are some of the properties of the solution? Well, the solution is in fact type 2, and the highest curvature occurs at the tip, and it blows up at the rate given here. Yeah, capital T minus T to the power of negative 1 minus 1 over n. So it's between so here it's between -0.5 and -1. It's a type 2 rate. And you can also one can also describe the solution in details. We will not do it here, but we just need to know that the solution near the tip region, the geometry looks like a bow soliton, a scaled copy of the bow soliton. And whereas the geometry near the neck region is modeled by the shrinking cylinder. And there is some intermediate profile that connects the bow soliton to the shrinking soliton, cylinder soliton. Okay, so this way we end up with a global solution to the mean curvature flow, which develops a type 2 singularity in finite time. And we can also consider odd integer m that's greater or equal to 3, and the solution will look like an asymmetric dumbbell, and something like this, and it forms a cusp sort of singularity. And if we apply a blowup analysis and base our point at the tip, then we will see again a bow soliton. Okay, in this case. So so this is the statement by Angen and Velasquez. And this concludes the part 1 of this talk. And then in the second half, we will look at the mean curvature flow solutions on non-compact hypersurfaces with a type 2 curvature blow-up.